Something about the sky feels off. Too many close grazes, too many anomalies in 1 month, and one day on the calendar that turns the whole topic from fear into rehearsal. Is this random noise, or a change in how we watch the cosmos? The numbers looked impossible at first glance. In a single September week, dozens of near-Earth objects skim inside the Moon's orbit. 2 are big enough to trend. 2025 RJ2 cuts within a fraction of lunar distance, and 2025 FA22 follows at just over twice that range. People point at the chart and say, "No way that's chance," but statistics with small counts are messy. It didn't sparkle. It screamed in ultraviolet. On September 11, 2025, SOHO's SWAN instrument caught a sudden Lyman alpha hydrogen flare, a comet announcing itself before most telescopes knew where to look. Within hours it was surging, its tail doubled overnight. Spectra showed a volatile-rich coma with hydrogen outpacing water, a red flag that the nucleus was cracking under solar heat. Each fissure popped like a vent, triggering step-like outbursts and fresh jets. Rubin Observatory diverted time. High-res spectrographs chased fleeting chemistry shifts, while a global amateur network fed precise timestamps to catch the spikes in real time. Models raised the stakes. The fractured core might not survive perihelion. If it breaks, the debris cloud could be spectacular from Earth and space. The lesson is blunt. Sometimes the first alarm is a hydrogen burst, and the fastest responders are thousands of eyes on the sky. Near-Earth approaches follow a Poisson process, the kind that bunches by accident. Clusters happen. What makes this one pop is our line of sight. Turn up the sensitivity and you discover a spike that was partly there all along. That doesn't mean nothing changed. It means our sampling did. And if the sky isn't busier, what changed? We did. The detection engine leveled up. Rubin Observatory's giant camera rakes the night into wide, fast tiles. Pan-STARRS, ATLAS, Catalina, and ZTF sweep from different longitudes, so the planet never really blinks. New software hunts faint streaks lost to human eyes. Track-linking algorithms stitch short trails into real orbits within hours. Even the ugly problems, trailing loss when fast movers smear out, and false positives from noise, are getting crushed by better filters and AI triage. For objects bigger than a delivery truck and within 1 lunar distance, catch rates now hover above 90% in favorable geometries. But physics still blocks one direction. Sunward approaches hide in daylight glare, where ground telescopes can't look. Infrared eyes in space solve that by spotting heat against the black. NEO Surveyor and ESA's planned NEO-MIR are designed for exactly this corridor. Until they're flying, one gap stays open. One gap still scares the pros. So what actually happens if one doesn't miss? Start with energy. Kinetic energy scales with mass and the square of speed. Double the speed, quadruple the punch. A stony object a little over 100 meters across hits the air at tens of kilometers per second. The air in front compresses, and the dynamic pressure spikes. When that pressure outruns the rock's strength, the body shatters in a high-altitude blast. Overpressure moves outward in a shock. Around a half psi can pop windows. A few psi can buckle light structures. The energy falls with distance, but an airburst at 10 to 20 kilometers altitude can rake a city with shattered glass and collapsing facades. Fast, loud, and confusing. Change the composition, and the script changes. An iron-rich intruder holds together longer, penetrates deeper, and can strike ground at near full speed. That's a crater, ejecta, and a thermal pulse that sets off secondary fires. Move the strike offshore, and you hand the energy to the ocean. Most of it dissipates in deep water, but near coasts, the coupling can stack into steep waves and dangerous surges, especially in bays and shallows. No villain, no intent. Just physics intersecting with where people live. Now meet a comet that announces itself in ultraviolet. It doesn't show up as a sparkle. It lights up as hydrogen. A space-based instrument tuned to Lyman alpha sees a surge. Ultraviolet photons from hydrogen atoms created when sunlight tears water molecules apart. That glow is a comet's breath, spread over millions of kilometers. Ground observers swing their scopes and confirm a fast brightening target. Overnight, the tail doubles. Spectra reveal a volatile cocktail. Water, sure, but also cyanogen and carbon-bearing gases that spike as the surface fractures under heat. Every fresh crack exposes ice that hasn't seen sunlight for ages, and outgassing leaps. Photochemistry does the rest. Water molecules fly from the nucleus at hundreds of meters per second to about a kilometer per second, then break into OH and H under sunlight, feeding that UV halo. Amateur observers time the steps in brightness and feed those timestamps into pro pipelines. That's how you catch outbursts, abrupt jumps that don't follow smooth heating curves. Sharp rises hint at vents popping open or small fragments peeling away. The word fragmentation stops being a rumor and starts to sound like a forecast. But the strangest chemistry belongs to a visitor that didn't form here. Some travelers carry a passport you can read in the math. C/2025 N1-3I/ATLAS arrives on a path that isn't bound to the sun. It's interstellar, and its chemistry refuses to play by solar system rules. In early spectra, carbon dioxide dominates, while water lags far behind. That flips the normal script. Then the nickel lines appear while iron stays muted. Nickel without iron isn't impossible, but it's rare, and it's a clue. Maybe the surface layers are coated with nickel-bearing organics that break down early. Maybe iron is locked in grains that don't vaporize under the same conditions. Maybe cosmic rays altered the outer crust during eons between stars, hardening some compounds and eroding others. Meanwhile, photometry and light curves suggest a slow spin, maybe even a wobble, non-principal axis rotation that changes which patches of ice see the sun. That makes the jets patchy and the brightness unpredictable. Small thrusts from those jets can nudge the orbit by tiny amounts, forcing modelers to add non-gravitational terms to keep the fit honest. Social feeds go wild with speculation. The data stay stubborn and weird. And while the chemistry debate rages, a date on the calendar turns fear into rehearsal. April 13, 2029 radiates in red on the whiteboards. Apophis misses Earth, safely, but slips inside the ring where many satellites live. The hazard score is 0. The science value is not. Earth's gravity will flex a rubble pile world, not enough to rip it apart, but enough to shake loose dust, rattle boulders, and tweak the spin. Think tides, but in rock instead of water. Those tiny landslides and dust plumes matter because they teach how force moves through a loosely bound body. OSIRIS APEX, NASA's repurposed OSIRIS-REx, will rendezvous near the encounter to capture what changes. Before and after images reveal how much regolith moved. Spectrometers check whether freshly exposed patches look different. Ground radar sculpts a shape model and watches the spin rate for subtle shifts. The result is a calibration set for the entire field. If you ever need to nudge a real threat, you want to know whether your push spreads through a gravel heap or sticks to a monolithic slab. Rehearsal only matters if we buy time. Time comes from two places: earlier detection and better playbooks. The proof of concept for deflection already happened. DART punched a small moonlet and changed its orbit measurably. The momentum boost exceeded the projectile alone because debris kicked backward, acting like a rocket plume. ESA's Hera mission will fly in to measure the crater, the mass, and the exact energy accounting. Vital details for scaling the method. Meanwhile, the Skywatch side needs its own boost. Infrared surveyors in space can see warm rocks against cold space even near the sun's glare, closing the most dangerous approach corridor. On the ground, planetary radar keeps its edge with bistatic setups. One dish transmits, another receives, to paint precise orbits for close passers. Emergency managers run drills that turn minutes of warning into action. Clear glass areas, shelter from shock, move away from windows, get critical infrastructure into safe mode. Critics argue about timelines and budgets. Program leads work within cost caps. But this isn't about winning debates. It's about shaving hours to days off discovery to alert. And every extra day turns panic into planning. So is this a pattern or a spotlight on our new vision? It can be both. Nature likes to clump. A breakup in the main belt can send a family of fragments earthward for a season. And orbital resonances can herd objects into planet-crossing lanes. We've seen families before, but we also just pointed better cameras with smarter software at the sky. The law of small numbers says you'll see spikes and lulls when sample sizes are tiny. As surveys mature, those spikes look less supernatural and more like statistics doing what statistics do. That's the perception shift. It feels like a storm because we finally have enough ink on the graph to see the weather. The smart move isn't arguing the vibe. It's funding the visibility and the response. Here's the bottom line. The September crowding wasn't a prophecy. The UV-Loud comet wasn't an omen. And the interstellar traveler wasn't a threat. Together, they're a lesson in attention. We built instruments that reveal what used to slip by. We built pipelines that turn blips into orbits before sunrise. We're about to watch gravity rearrange an asteroid in real time and record every scar. The sky was always this busy. We're finally busy enough to keep up. The next headline could be a harmless fireball that rattles windows, a bright comet that fragments gracefully, or a close pass that proves our alert system works. The only thing that turns any of those into a crisis is a lack of time. So buy time. Keep the cadence high. Close the sunward gap. Train the people who flip the switches. And when the numbers jump on your feed, read them with calm precision, not panic. Because coincidence or pattern, this is the era when we stop being bystanders and start being ready.